Greetings, fellow knowledge seekers. Welcome to PaperLedge, where we dust off the ivory tower and bring cutting-edge academic research to your ears. I'm Ernis, your friendly neighborhood explainer. Today, we're diving headfirst into a fascinating paper that asks, can LLMs, those AI brains behind chatbots and text generators, understand how a robot understands its world? Sounds a bit meta, right? Well, buckle up, because we're about to find out. This paper, titled, Can LLMs Translate Human Instructions into a Reinforcement Learning Agent's Internal Emergent Symbolic Representation? Is by Ma, Nguyen, and Xu. The researchers are at the U2I, ENSTA, IPPA, and they tackle a fascinating question: can we use LLMs to bridge the gap between how we humans describe tasks and how a learning robot thinks about them? Now, before your brain starts doing somersaults, let's break this down. Feynman style. Simple, clear, and with a dash of cosmic wonder. Picture this. You're teaching a puppy tricks. You say, sit, the puppy eventually understands. But what's going on inside its furry little head? Is it the same, sit, we understand? That's kinda what this paper is about, but with robots and complex instructions. The researchers used a reinforcement learning agent. Think of it as a robot puppy learning through trial and error, in two environments, an ant maze and an ant-fall scenario. Okay, let's construct our memory palace. Imagine a vast, digital cityscape. The first building we enter is the ant maze. Picture a robotic ant navigating a twisty, superset-shaped corridor. Our second stop is the ant-fall building, where the same ant has to push a block into a pit to create a bridge. Dramatic, right? So, what did the researchers actually do? Well, they used something called the STAR algorithm, spatio-temporal abstraction via reachability. It's a fancy way of saying the robot learns to divide its environment into meaningful chunks, like rooms in a house. These chunks, or regions, become the robot's internal symbolic representation, its way of understanding the world. It's like the puppy understanding. Sit means putting its bum on the ground. But here's the kicker. This representation changes as the robot learns. At first, it might see the maze as one big blur, then slowly differentiate areas as it explores. You might be wondering, where do the LLMs come in? That's the clever bit. The researchers asked humans to give instructions to the robot, like, move right until you completely pass the wall on your left. Then, they fed these instructions, along with the robot's internal representation, to various LLMs, GPT, Claude, DeepSeek and Grok. The LLM's task? To translate the human instructions into the robot's language, the sequence of regions it needs to traverse. Think of it as the LLM being a Rosetta Stone, translating human speak into robot speak. But here's where things get interesting, and a little Rick Sanchez-esque. The LLMs weren't always great at this translation. Their performance depended heavily on two things: the granularity of the robot's internal representation and the complexity of the task. In the ant maze, as the robot learned and divided the maze into more and more regions, the LLMs actually got worse at understanding the instructions. Fine. Yeah, I guess. It's like trying to explain something to someone using increasingly complicated jargon. Eventually, they just glaze over. But in the ant-fall scenario, something surprising happened. The LLMs' performance initially dropped, then partially recovered. Why? Well, the researchers think it's because ant-fall involves not just navigation, but also object manipulation, pushing the block. This added complexity might have forced the LLMs to think a bit harder, leading to some improvement. Now, let's delve into the nitty-gritty. To evaluate how well the LLMs were doing, the researchers used something called GBLE score. It's a way of measuring how similar the LLM's translated instructions are to what a human expert would expect. The results? Well, let's just say the LLMs aren't quite ready to replace robot driving instructors just yet. While they showed some ability to translate human instructions, their performance was inconsistent. They struggled when the robot's understanding of the environment became too detailed. And they didn't always leverage the robot's internal representation effectively. It's almost as if the LLMs were relying on surface-level patterns in the instructions rather than truly understanding what the robot was thinking. As the researchers themselves put it, there's a lack of stable alignment between human language and symbolic plans. So, what's the big takeaway here? Well, this paper highlights the challenges of bridging the gap between human communication and AI understanding. It suggests that current LLMs, while impressive, still have limitations when it comes to truly grasping the internal representations of learning agents. But don't despair, my curious companions. This research opens up exciting avenues for future exploration. Imagine a future where we can seamlessly communicate with robots, guiding them through complex tasks with intuitive language. That future might be closer than we think, thanks to research like this. And that, my friends, is the essence of this fascinating paper. A reminder that even the smartest AI still has a lot to learn about how we, and other intelligent agents, understand the world. Now, go forth and ponder the mysteries of minds, both human and artificial. And until next time, keep exploring the PaperLedge,